Hi everyone, in 3.2 we're going to do something that at least for these first few examples might seem kind of silly, but it's going to be some really useful stuff that we're practicing for some of the sections that are coming up, so just bear with me. We want to look at how we would use calculus to find the area or volume of different shapes. And in particular for a rectangle, this is especially silly, but I just want to build this up because, like I said, we're going to be using this later. We're going to add multiple levels of complexity to what we're doing here. So at first it seems silly, but it'll be really important later. Okay, so what I want to do in this section is I want to take whatever shape it is we're working on, and I want to split it into little quote-unquote manageable pieces. Again, this is kind of silly because a rectangle is pretty manageable as is, but we're still going to look at how we could break this up into infinitely small pieces and add them up to get the total area. Okay, so one thing is we know what the answer should be. We'll know if we've messed up or not because I know that the area of that thing is in fact 40. So here's how we're going to do this. We're going to slice this up into little infinitely skinny rectangles, and this is why the rectangle is particularly silly, because we're going to use the formula for the area of the rectangle when we set up the integral. So I think the hardest part of the section for people is that you have a lot of freedom. You get to choose what your variable is, which direction you're slicing. Sometimes it matters, sometimes it doesn't. So rectangle, I think I'm going to slice vertically. I'll try and switch it up and do both. I have a lot where I like horizontal, but generally either will work. Okay, so there's my slice, and I'm going to imagine that that slice is going to become infinitely small. I'm going to go ahead and name the width of this, and it doesn't matter, you pick what you want. So I'm going to call it, I don't know, delta z. And then this is the step that people actually really struggle with, and it's an important one. That's fine, you can call that whatever you want, it should have a delta. But from here, you need to then clearly define what your z is. And what I would say is we've said that that's a delta z, which is a little tiny horizontal distance. So whatever your actual z variable is, it better be measuring horizontal distance. The other thing that I would say is that in order to do this, you need to pick a fixed point. Basically what the z variable is telling us is where our slice is. So pick a really nice, easy to define fixed point in this picture. Generally I would say the far left or right hand sides, or if you're slicing horizontally, the top or bottom of the shape are good. Sometimes it makes sense to start in the middle. It really is your choice, so just carefully pick, make sure you're thinking the right direction. If delta z is horizontal, then z better be horizontal. So I'm going to say that z is the distance from the left hand side. Okay. So what I want to do is say, okay, if I look at this little rectangle that I just drew, the area, I'll call it an a sub I, the area of my ith slice is going to be delta z wide and 4 high. So this is one nice simple thing in this problem. The height of the slice never changes. That's what makes the rectangle really simple. It's basically like integrating a constant function, y equals 4. So if I want to get the total area, I'm going to add all of these up. So I'm going to say I have the sum of the 4 delta z's from I equals 1 to n, and then I'm going to let n go to infinity. We don't have to write this out every time, but I want you to still think about how this builds up, which means that the area is actually going to be the integral of 4 dz, and we can look back at this and say, okay, now we need to think about, instead of just how many subintervals, how many slices, we need to think about the beginning and ending values of z. So if I want to get exactly this entire rectangle that I have sitting there, I better start at z equals 0, so I'm starting at the far left hand side, and I better stop at the far right hand side, which is 10 units away. So this turns into a 4z, antiderivative of 4 is 4z from 0 to 10, which ends up being 10 times 4, 40, minus 0 times 4, 0. So there's our 40 centimeters squared. Looking back in the integral, notice that the units come from the 4 and the dz. Those are both in centimeters. Okay, so again, rectangle in particular seems kind of silly, but I promise we will use this in situations where it's not just silliness to slice up a rectangle and add up little rectangles to find the area of the big rectangle. Thanks for watching.